All right, so I am now again going to try to talk about 7.3, and we were looking at composite values, which I prefer over the word variables. And the idea is in an array, we had a situation where you could have some sort of a base like A, and then you could use a number to indicate how far down, you always had to start with 0, how far down you wanted to go into the array. And that worked because every item in an array is the same width. Okay? There's a different type of composite value called a record. And this is not going to really allow us to use indexes easily, because this is where the values, the parts are different sizes. So in an array, parts are all the same size. The parts are the same size. Pretty much that's the important part. Over here the parts are different. Pardon the messy handwriting. As an example, consider the case of a person, right? I might want to have a data structure to represent a person, an employee. That's what your book does, employee. So I'll try to follow your book. And your book says an employee has a couple of fields. It has a name. An employee has, I'm going to put them in little boxes here, an age, and it has, let's just say a wage. They put hourly wage in your book. So how much you would want to pay your employee. And each one of these fields for an employee can be of a different type, which means you might want to represent it differently. For instance, an employee's name might require you to use some number, maybe 15 different characters to represent it. Can you think of a name with 15 characters? My son's here.
I don't know.
Let's see. Let's just try a name. Let's say like Jennifer. How many N's do you think there are in Jennifer? I put 2 N's. You know, some people always like to invent new ways to spell their name. So that's 1, 2, 3, 4, 5, 6, 7, 8. You know, but you can imagine some names. I used to have a student named Sethurama Pamachandran.
Really?
Yes. So some names could get quite long, so you might want to reserve enough characters in order to write every name, and then with a string, in order to indicate that there's no character there, you put a /0. Right? That's special, that if you put in quotes, if you write /0, that means you're storing a hexadecimal 0 byte. So it's all zeros. In binary, that would just be 8 zeros. And that's used to indicate the end of a string. It's called, sometimes we call that null, and we say this is a null terminated string. So, but you would need, I guess, from 0 to 14 characters. So you need 15 different characters, a size of 15 for that field. But for the age of a person, how old can people get? I think 121 is the oldest person ever. And for that one, you would really only need 7 bytes. But we like to keep things in 8-bit increments because that works better with the memory. So for instance, I probably would want to use 16 different positions for the name. And let's see, you wouldn't want to use 8 bytes. You'd want to use 8 bits, because 8 bits can go from 0 to 256. So this age field only requires 2 bytes. So that's a much different size than the name. So age only needs 2 bytes. That is, age only needs 1 byte. 1 byte will let you go from 0 to 255. Right. Whereas name might require 15 or 16 bytes, because each character is a byte. So here, this field is a much different size. Age is a much different size than name. And how much you're going to pay a person, usually we represent floating point numbers. So a wage might be in dollars, right? But sometimes it's easy to use something called a fixed point thing. So if you're going to pay them $123.76, we represent that as an integer. We just write 12,376 pennies. And then we print it, we'll put a decimal point in the right spot. So we always know that there are going to be 2 digits to the right of a decimal point, and then this is called a fixed place, or fixed precision. Precision is the number of characters after the decimal point. Okay. So we can actually represent the amount that a person earns as dollars using really what we only have to store is just like any whole number. And we just pretend that there's a decimal point 2 positions back. So if we use, so generally wages are always going to be positive, so we can store that in 2 bytes. And 2 bytes goes up to, I think it's like 0 to 64,000 something, basically 64K. And is that right? I think it's 640,000. I had better check on that real quick. 2 to the 16th is 65,536. 65,536, which means that if I only used 2 bytes to store the wage, the most I could ever pay somebody is $655. But this is supposed to be per hour. So I think that's pretty realistic. I think unless you're Bill Gates, you don't earn more than $655 an hour.
I guess.
Yeah, but if I needed to have a bigger number than that, I might want to go to a 4-byte number. And for that, that's a 32-bit number, and 32-bit unsigned numbers can go all the way up to, let me calculate it over here on the computer. I wrote the wrong thing. 2 to the 32nd is, there we go. If I use 4 bytes, then I can go all the way up to whatever this number is, 429496726 minus 1, 5. So this is pretty good because if I put the decimal point in the right spot, you could earn $42 million an hour, and I could store the wage that way. Right? So I can use a 32-bit number, and that's 4 bytes. So I think the important point here is that we have now a record that is, each element is a different size. The first element might be 16 bytes, the second might be 1 byte, and the third it might be 4 bytes. And so this idea from an array of being able to simply add some multiple of the element size to get to each position won't work unless we were to pad things and waste memory like we did with strings. Right? So the solution, the difference here is that each element is a different size. And what we do is you can kind of store the offset. So if you have a pointer to the beginning of the employee, you can store some variable called name. And I'm going to write it all in uppercase here to indicate that this is some sort of a constant thing. And then you can say employee plus whatever the offset is to name, and that gets you to the name. And you can say employee, if I write it, I'm just going to write EMP. How about that? Because I can't do it. EMP plus age. That would get you the address of the employee's age. So again, let's imagine that this employee was sitting in memory at some address. Maybe the address there is 0x0A00. Right? and I wanted to access the age. Well, the age is going to be at offset 15. So somewhere I might set age gets the value 15, which is a F in hexadecimal. So employee plus age gives me the address of that age variable. It's 15 bytes past the beginning of the employee. Similarly, employee plus wage, so the wage would be not at offset 15, but this would be at offset 16. So I would store somewhere that wage is an offset of 16, right? So in hex, this would be an F and this would be a 10, right? So if I wanted to access the wage, the address of the current employee's wage, so there's an employee in memory at A00, his wage is going to be at A0A10. And his wage would be there, and his age would be at address 0A0F. Pretty interesting, huh? So I can calculate the address in memory by just kind of keeping the offset to each field in some sort of a named variable. But this gets confusing because it's got a plus sign and we think that that's addition. We kind of think we're adding the values instead of the addresses. So what we do for notation, people have come up with different notations, but the most common notation for this is to say employee dot wage. And what that means is take whatever offset wage is and add it to this base address. And that will give you kind of the address of the wage for that employee. Or we might say employee dot age, and that gives you the address of the employee's age. Or employee dot name, right? So name, the offset to get to the name is 0. That's the very first field. Right? So these things aren't all equally spaced, these offsets. And we can say employee.name, employee.wage, or employee.age to basically add the address of your employee plus the address of the name. Okay. So this kind of notation is used for record. And each record we've now kind of defined sort of, you can think of it as a new composite type called employee. And the size of this data type is going to be 16, 17, 21 bytes for each one. And if I wanted to, I could have a whole array of employees. So if I wanted a list of employees in a database, and each employee record would require me to store 20 or to have 21 bytes. And then for any given employee, if I get the address of that employee, I can calculate the offset to his name, age, or his wage, and then I can proceed to calculate from that. So I hope that was maybe clarifying and not confusing. We tend to not want to work at this level of remembering that these fields are just sort of named offsets from a base address. It's important to have that concept in mind, but again, we always like to operate at a higher level when we're writing pseudocode. And so in your pseudocode, you're going to do something more like saying employee. So the convention here is when we're using some sort of a more complicated type of value, that we're going to list the type of the value first. So we're saying, I'm about to tell you that there's an employee, and his name is EMP. So I've just basically said there's a new variable called employee. And the assumption is that out in memory somewhere, you're going to construct this record that has a name, age, and wage that are of the kind of appropriate sizes, right? Out in memory somewhere. All you have to do is write that, and it kind of implies that you've gone out and you've allocated this much space. This is called a declaration. And what it means is reserve 21 bytes. That's all it really means. Reserve 21 bytes. And at least at this point, that's all it means. So now I can begin to manipulate this employee. So I could say something like in pseudocode, set emp.name to, and I'll just use the string Joe. So when you type in a string Joe like that, what it's going to want to do is what you're saying. This is a shorthand for take this string and write in J O E, and at the end of every string there's a secret. You're just going to pad it with zeros at the end. You always have to end a string with a null. And we can say set emp, and this is kind of the simpler notation that's closer to how it's easy to think of things. So say he's 37 years old, right? So then they'll come over here, and you'll set that to the appropriate value, right? The appropriate number of bits. Right? And we can say set emp.wage to 2750. And like I said, we might store the value 2,750 here, but we're understanding that there is a fixed place decimal point there. So this is all you'd have to write in your pseudocode. And it is important, though. I mean, this is all you should write in your pseudocode, because this is kind of the high level way of thinking of things. And this is maybe the details of how that's likely to get implemented, and understanding these details is just supposed to give you some sort of a rationale of why we call this thing a record, why it's different than an array, right, and why we use this type of notation. Okay. So that actually that wraps up 7.3. Next we're going to talk about 7.4, where we'll look at some searching algorithms. I do want to point out that you can actually have an array of records, right? So you could have, remember each record is 21 bytes, so you could have an array of records. So maybe this is my array A, and then each item in the array, so at index 0, that is 21 bytes, right? So that 21 bytes could be an employee, right? So A0 dot name, A0 dot age, and A0 dot wage would just be offsets from A0. So you could say A bracket 0 dot name in your pseudocode to indicate this address. I could have somewhere here at index I. In order to get there, I take A0 and I add I times 21 to get me an address right here. And if I want to access the right here, there's 21 bytes being stored, all jagged, with name, age, and wage. And if I wanted to access the age of that person, what I would write is something like AI dot age. Okay, and what that would imply is find the offset to this record, which is right here, and add to that the offset that points at the age. And that would get you this field right here. Yeah, I mean, this is looking a lot more like a database. You'll notice if you ever do any database programming, for things like strings, they usually ask you to give a max length for the string. Sometimes you'll have a variable length string, but I think that really amounts to something more complex. So, but very often you have strings that can go from 0 to 15 or 0 to 256. So there's some limit on how long most strings can be. And this is why. All right.